And I'm live! Yay! You guys should all be able to see me. Give me a heads up on the, give me a thumbs up on the Google Meet if you can see me. How big's the delay gonna be? The delay's gonna be really big. It's gonna be like 3 minutes or something. My laptop's doing an awful lot of work here. Poor little laptop. I'm waiting for the first thumbs up. Who's gonna give me the thumbs up first? And I'm live! Oh, there you go, there's. Okay. You guys should all be able to see me. Give me a heads up on the, give me a thumbs up on the Google Meet if you can see me. Stop. There we go. Yeah, we're all in. Right. So chat's all running. There is a still huge delay, but it's okay. I don't know who Epicos is and Niazin. I don't know who that is. Don't know who any of those people are, but all right. Right. Okay. Right. I'm going to share my screen with you guys. Share screen. I'm going to share that one. Boom, we're up and running. Hide that, go for that one. Yay, amazing. Right, we're in. Right, guys, zoom, zoom. So here's today's lesson. Okay, so today's lesson, we're gonna be looking at using KOFS. Yeah, sorry, I muted myself by accident. I didn't mean to. I didn't mean to. Okay, back, I'm back. Okay, thank you, Sian. Got 3 minutes of nothing there, that's excellent. So as I said, we're gonna be focusing today on KOFS and explaining shift and end result on yield. Now, so first learning objective, know what KOFS stands for. Gonna remind us of that one, we did it last lesson, but it's a good recap. Number two, be able to use KOFS to explain shift and all the scenarios and know the conditions for some industrial equilibriums. Okay, so now the first thing we need to do in this particular scenario is we need to remind ourselves that this is all about questions in the exam. So question number one, explain. I've suddenly realized how big my writing is compared to my text. So I will, oh no, I quite like that size actually. Question number one. So, explain effect on yield. Explain effect on yield when, let's go for temperature first, when temp is decreased. Now what they will do is, of course, they will also give you an equation. I should have actually given you the equation first. In the exam, they give you the equation, they give you a bit of blurb, and then they'll give you the question. So let's just choose a particular equilibrium. I'm going to try and choose equilibriums that you guys need to know about. So in this case, I'm going to go for SO2 plus half O2 goes to SO3. And this is going to be, now that'll be interesting to look up whether or not it's endo or exo. I don't like the idea of, no, I'm pretty sure it's exo. It's an oxidation. It's a combustion. So this is going to be minus, let's, oh, I hate quoting values if I don't know it. So let's just check the value on that. So we want SO2 to SO3, enthalpy change. Enthalpy change, go. Is going to be minus 98 kilojoules per mole. I love it. Minus 98 kilojoules per mole. Yep, cool. So they're going to give you that information. And the first thing we're going to do is run KOFS. Yeah, KOFSy if you like. So the first step, of course, now I'm just going to run this one for you guys. Then I'm going to give you another temperature one to have a go at. Yeah, and we'll add on all the extra bits of details. This is actually part of industry as well. So this particular equation, this one here is used in industry. Oh, by the way, it is in equilibrium. I do apologize. This is the contact process. Contact process, which is used to make sulfuric acid, H2SO4. I'll give you that in its entirety if you like. But this is the bit that we need. So we've said the effect of when temperature is decreased. Right, so we're going to run KOFS on this. So K, which is our knowledge. Yeah, I put underneath it knowledge. And we remember this comes from the equation. Yeah, if you want to make that note, you can do. Knowledge from equation. From equation. It's French for equation. Knowledge from the equation. So first thing is, because this is to do with temperature, I highlight temperature, yet the bit of information is going to be this guy. Yeah, and it's telling us, so first, and this is the hardest one, guys, is being able to identify from the question which part of the equation they're wanting you to use. So in this case, the knowledge here for temperature is always, is it endo or exo? So we're going to say knowledge. Forward reaction is exothermic. Okay, next, oppose. This is the most lost mark in AS chemistry. And because the problem is students will say, Le Chatelier's principle says that it will oppose any changes on it. No, what you have to say is we decreased temperature. Temperature, it's coming from the question now. Yeah, temperature is decreased. So equilibrium, you're saying what you did and what the equilibrium will therefore do. And it's just the opposite. If we decreased, so equilibrium will increase temperature. Increase temp. Next, okay, now that we've said what the equilibrium is going to do, we need to say how it's going to do it. And the F stands for favor. So how is it going to do this? Equilibrium will favor, it wants to increase the temperature. Yeah, so it's going to favor the hot reaction. So it will favor exothermic reaction. Now we know that's the forward one. That's the part from the knowledge. Yeah, then we're going to do shift. S stands for shift. So if we're going to favor the exothermic reaction, which is that one, the equilibrium is going to shift from left to right. Shift. Equilibrium will shift from left to right. Don't know why I capitalized. And the last one, KOFSy, if you like, yield. Yeah. Yield of SO3 will increase. Cool. So KOFS is a process you genuinely have to practice. It's very, very easy. It's very easy for students who they don't practice and they shortcut it. You cannot shortcut KOFSy. Yeah, you can't shortcut KOFS. It's important that you understand that. You don't know which mark they don't want you to do. I just need you guys to be running it in its entirety, no matter how many marks it's worth. You've got to run it in its entirety. Okay, so we've just done temperature. Let me give you an alternative question. Okay, and we're going to come back, by the way, to the contact process because there's a whole load of cool clauses in this, but we're focusing today on using KOFS. So let's do another temperature one. Right, this is for you guys to now have a go at. Okay, question number 2. This is for you guys to run. Okay, so I'm going to give you another equilibrium. Let's do. Okay. Okay, first question on the chat. I'm going to actually flag these as all gases, by the way. There we go. First question on the chat, please. Year 12. Impress me, folks. Can someone on the chat please name me that, please? So I'm going to call this one A. Can someone then name for me B? And then can someone also name C? I wonder how many people can get all of those right. Right, now I need to give you some information on this in terms of endo or exo. This is positive. It's about 43, I believe. So, right? Something like that. 43 kilojoules per mole. Okay. Sian, well done. Thank you very much. A is correct. That is ethanol. It's nice to have that. Sian's then followed it up with B. Good job. That is ethene. She knows her organics. I love that. The last one is water. Vapor. Thanks, Jim Joe. Yeah, you've got to remember, guys, C is not water. Yeah, C is steam or water vapor. If you call it water, you've lost the mark. Yeah, they love doing that, folks. They love doing that. It's one of the key things that they're always checking. Yeah, it's a clever game. It's all a trap. Right. So what I'm going to do is we are going to, okay, so let's, here's your question. I'm going to do the question in blue. So question, we're going to increase temperature. Increase temp. What's going to happen? What effect on yield of ethene? Off you go, folks. Can you please run KOFS for me? At this point, can I ask you to do me a favor? Can you, now the problem is this is going to then put me immediately out of sync, which is a nightmare of this. So what I'm going to do is I'm going to leave that question for you guys to complete on the chat, and I'm going to begin writing the next question. Okay, so A, increased temperature. B, nope, don't know that either. I love that Oliver's image in a, you are talking, your mic is off. Oh, my mic's off? How has it gone and done that? Oh, it's because of my, it's the other thing. Oh, we've got an answer. I like it. Forward reaction is endothermic. Cool. Let's check this as we go. So I'm going to write down Shaz's answer. We can scrutinize it. Knowledge. Forward reaction is endo. I like it. Forward reaction endo. Well done. Spot on. That is correct. Based on that bit of knowledge, that symbol right there means endo. Next. Oh, why do you keep retracting it, Shazza? Put it back. Put the answer back, Shazza. Oh, I wanted it. You can check your own, I guess. Oppose. Right, hang on. What did we do? Increase temp. So we increased temp. Therefore, equilibrium will reduce temp. I like it. Next, favor. How's it going to do that? It wants to lower the temperature. There we go. I love it. Equilibrium will decrease temp. Yes. Favor endothermic. Spot on. Yes. Favor endo. Shift. Right, so if it's favoring the endo, it's going in that direction. So it's going to shift it from left to right. Shift left to right. Is that what he said? Shift L to R. I'm cheating here. Shift left to right. Yeah. Yield increases. Love it. Yield increase. Love it. Well done, Shazza. Full marks. Love it. Outstanding. I love that, Oliver. Again, your picture keeps freezing. It's because you've got your stupid chemistry lab in the background. Right. So can I please have a quick, and I know that there's still this delay, even though I can see you guys, and it's nice to have you guys there. The delay, I thought it was going to get rid of the delay, and it hasn't. Give me a thumbs up if everyone got it. In fact, on the chat, please give me a thumbs up. Use your emojis. Yeah, give me an emoji if you custom emoji. There's custom emojis. I don't know what custom emojis are. Oh, there's a thumbs up. Where's thumbs up? I can't see a thumbs up. I can dab. Oh no, dab. I'm dabbing 3 times. Yeah, nailed it. I don't know where the thumbs up is. Where's the thumbs up? There must be a thumbs up here somewhere. I need the thumbs up. I think it's important. Spending my time on YouTube trying to find thumbs up emojis. No, there it is. Oh, I've lost it. Thumbs up. I like it. There is an emoji. I promise you there's an emoji. I'm trying to find it now. Can't find it. There. Found it. Yes. Go. Send. There we go. It is there. Yeah. Okay. Now, the next question was suggested temperature. It's always nice to talk about this. So, how about 1,000,000 degrees? That's a good idea, isn't it? Because it makes sense. Like, higher temperature means that we get a bigger yield. Yeah? So, why not 1,000,000 degrees? Why is that a bad idea? Yeah, Oliver, you need to turn off your lab thing. I've just looked up and your picture's changed. Have you ever seen the episode of have you ever seen Doctor Who? Doctor Who has an episode called The Weeping Angels, and you're doing exactly what they did on that TV show. It's where they move when you're not looking. That's what's happening. It's freaking me out a little bit. Anyway, so why would 1,000,000 degrees be a really bad idea? So suggested temperature, anywhere between 450 and 650. That'd be a reasonable temperature for this reaction. Now, the reason why is because of damage to equipment. Yeah, we realize you just can't just keep increasing the temperature. Bonds will break. Oh, thermal decomposition. Yeah, absolutely. Yeah, damage to equipment and thermal decomposition. You're absolutely right. That will happen, Sian. Yes, bonds will break. You decompose all your compounds and then not get what you want. Yeah, for sure. It's nice to mention industrial temperatures. They tend to range. In fact, the range for industrial temperatures that you need to know ranges from 300. I'm trying to think of the highest temperature I know for an equilibrium. 450. It's as high as they go. Amazingly. Which is quite nice to do. So in this case, it's talking about the damage to equipment, yeah, cost of the equipment to cope with such high temperatures, etc., etc. Cool. Right. I think if I've got thumbs up from everybody, we can move on to pressure. Now, I'm going to, again, run an example. This is where I need to figure out what size my writing should be. Okay, question number 3. Let's run pressure. So let's do the same one, because this one you actually need to know. So this one, I'm going to reverse the equation. ethene plus steam goes to ethanol. Goes to ethanol. I like it, and that's a gas as well. Right. So I'm going to tell you that that forward reaction is minus 43 kilojoules per mole. And I'm going to say, question A, I'm going to increase, do you know what? Let's make it harder. Oh no, let's keep it easy first. Increase temp, ... yield of ethanol? Explain. I like it. Right, guys, let's run KOFS. So knowledge. Now, this is the thing. Each different equilibrium change has a different knowledge from the equation. And I ought to actually make a list of these. That would probably be quite useful. So you can put them up here. So we know factors. You can just put this as a nota bene if you like in your note. Factors for equilibrium shift. We know these. Number one, temperature, temp. Knowledge, the K from KOFS, yeah. The knowledge here for temperature is forward reaction endo-exo. Yeah, that's the knowledge. Plus delta H, minus delta H. There's the knowledge. The next one, number two, is pressure. Number two is pressure. Oh, I shouldn't do that. I should line it up so I can do it like a table. Number two is pressure. So the knowledge from KOFS is X moles of gas on left, Y moles of gas on right. You realize that X and Y are just numbers. Yeah, these guys here are just numbers from the equation. Yeah, numbers from equation. Okay, number three, concentration. 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 Okay, so concentration for KOFS, for knowledge, is X is a reactant / product. Yeah, that's it. And we'll come back to that in a minute. That's a really useful box to have. I'm not going to lie. That there is an amazing nota bene. It's beautiful. It's some beautiful chemistry. It's gorgeous chemistry. Yeah, definitely put that in your notes. It's super handy. So in this case, we're now talking about, oh, we're doing temperature again. Doing temp again. Cool. So run it. KOFS. I would recommend an exam, by the way I do this on an exam. So if I'd had my page here, you know, there's borders on the page. I'd have written KOFS in the back in the border because they're not going to mark that. And then I run the bullet points next door. Yeah. So knowledge, forward reaction is, and there it is. There's my bit of info. Is exothermic. Next, what did we do? We increased temperature. We increased temp. Therefore, equilibrium decreased temp. Decreased temp. Favors. How's it going to do that? Favor endo. Reaction, equilibrium will favor endo. Equilibrium. Hang on a minute. Equilibrium will favor endo because endo is cold. Favor endothermic reaction. Endo reaction. Shift. Right, which one's the endo? That one. Yeah, because if that's the exo, If this is exo, because of that bit of knowledge, the other one then must be endo with the exact opposite value. So I'm going to shift from right to left. On the chat, please give me a thumbs up if you got it. Oh, if I haven't finished. Yield. Right, what did I ask? And yield of ethanol. Yield decrease. KOFS, yield decrease. I like it. Give me a thumbs up if you got it, folks. In fact, instead of a thumbs up, because the thumbs up was the right one for the other question, you can give me another emoji. Give me like a, I don't know, give me a monkey. Oh, look, Schrodinger's cat in a box. Why on earth do I have Schrodinger's cat in a box? Give me a cat in a box if you got it right. If you didn't, give me any other emoji. Okay, so we've run KOFS on 2 temperature ones. Now we want to switch to pressure. And I'm going to stick with the same example because this is another important one for you to know. Love it. No one's giving me a cat in a box. Oh, why the cat? I'm just, do you know what? I've separated it with a cat in a box, haven't I? So it's fine. Oh, I got a monkey. I got a monkey. Shaz, Oliver's giving me a monkey. Shaz is giving me a monkey with its eyes covered. It's all very weird. Number 4. Question number 4. Q4. Okay, let's stick with the same thing. By the way, if you're interested, this particular one is rather interesting in terms of suddenly realize there's a nota bene that goes on this particular question. The temperature used in industry, temp used, is 300 Celsius. That's pretty hot in my opinion. So hang on. The problem is that KOFS is telling me, KOFS is saying favor equilibrium. Oh, hang on. Increase test, decrease yield. So hang on a minute. We increased it, the temperature decreases it, and I get more. So what we need to do is the opposite. So we need to cool this. The colder we have, the more yield. So why 300? This is odd. So hang on a sec. Why is it that we should be going cold? This is odd. We should be cooling. We should be cooling this reaction. If we cool it, we get a greater yield. But we're still running it at 300. Sian, can you tell me why? Why so hot? I'll leave you to think about that one. Right, question number 4. Ethene plus steam goes to ethanol. Okay. Question. No, I don't want to jump the gun here and get it. It's going to get more difficult, you see. We increase pressure. Yield? Question mark. Explain. Sian's ignoring me entirely. I've just had a... Okay. Sian, are you there? I don't know. Okay. Does anyone else know? Jim Joe, do you know? It's a massive delay. Massive. It's okay. Pressure? No. Why so hot? Okay, guys, the reason why we want it so hot, why so hot? Answer. Rate. if we cool it too much, the rate of reaction slows down. So 300 degrees, yield of what? Yield of ethanol. It's always about the product, Jim Joe. It's always about the product. Glad you asked. The rate of reaction slows down. Compromise. Yeah, we want a good yield at a fast rate. Now, there is understanding to that, and I can actually teach it. I can. It's just a bit messy. Okay, I'll give it a go. So, okay, guys, I just want you to put your pens down for a minute. So what we're going to do is we're going to do a really this is purely for understanding compromise. I'm going to turn A into B in an equilibrium. Now we're trying to make B. B is the product. Yeah, that's what we want. So what we're going to do is I'm going to tell you that the forward reaction is exothermic and the backward reaction is endothermic. Now, what that means is if we were going to run this at temperatures, what we're going to want to do in order to favor this reaction, we'd need to do the opposite of what the equilibrium is doing, which is getting hot. That there is the hot symbol. Yeah. So what we're going to have to do is temperature should be low. And so let's choose a number. Let's go for 400 Celsius. Now that's not low temperature. Yeah. And what we're now going to do is look at the yield. Yeah. The yield of this reaction. And then we're going to look at the time it took to make it. Yeah. So at 400 degrees Celsius, the yield is 10%. That is really bad. Like uber bad. Not even grab bad, but uber bad. Yeah. But the time to make it was 30 minutes. Yeah, it was really quick. Yeah. So at this point, they look at the yield and go, it's a terrible yield. Yeah. So let's lower the temperature. Let's go to 300 degrees. So we go to 300 degrees and the yield jumps to 30%. Now this time, because we've now lowered the temperature, the time to make that is going to increase. And the time now goes to 45 minutes. Yeah. Now at this point you go, right, was that worth it? Well, I have increased the yield by 3 times, but only increased the time by 50%. I've increased that by 0.5. So what that means is that is definitely worthwhile doing. Yeah, there's a balance here. It takes more time, but I'm getting 3 times more out on each pass. Now at this point you go, oh, hang on a sec. Let's lower the temperature even further. Let's go to 200 degrees Celsius. Now when we go to 200 degrees, I now have a 40% yield increase. So I now got 40% yield. I've gone up by another 10%. But this time it's going to take me an hour. It's going to take me 60 minutes. Now the question is, was it worth it? So I'm going to get an extra 25%. I'm going to get an extra 25% yield. Is that right? Or an extra 10% yield. I should have done that one. So I've got an extra 10% yield, but it's taken me an extra 15 minutes. So hang on a minute. Let's say I got 30%. I've given really awkward numbers here. It's not really a good answer. Let's say it takes me 2 hours, or let's say 120 minutes. Right, was it worth it? No, I want to go for easier numbers. 90 minutes, that's easier numbers. Because the 90, I've doubled the amount of time, but I'm only making an extra 10%. Yeah, I've only, yeah, times 1.5, 1.25 even, yes. 20%, 25% of the 30%. Yeah, because, yeah, I know. It's all, I've done terrible numbers. So that there, not worth it. Not worth it. The reason being is what I'll do is I'll take the 30% and then I'll just run the whole thing again. Yeah, so if I ran that experiment twice, I'm going to run that one, run this twice. Because if I run that twice, it's the same amount of time. But instead of getting only an extra 10%, I'm going to get 30% again. Wait, no, it isn't. Yeah, so and it's because I'm changing all my numbers. I'm sorry, I've not done that particularly well. I should have always tried to aim for easy numbers. And that's bad teaching that. I apologize for that, folks. But that's not worth it because you'll just run the experiment twice and you'll get more yield out. So again, it's understanding this term compromise, which is a reasonable yield at a reasonable rate. Yeah, compromise. And those words you should always write down. Reasonable yield, reasonable rate. Yeah, it's the compromise, it's the balance. Cool. Okay, so this one, pressure. Right, let's run KOFS on it, folks. Let's run KOFSy. Yeah, KOFSy. Okay, so knowledge. Now, we learned earlier in the lesson that the knowledge part of this for pressure is moles of gas on the left and moles of gas on the right. Right. So how many moles of gas do I have on the left? So I've got 1 mole of gas there, 1 mole of gas there. The total is 2 moles on the left. And on this side, 1 mole of gas only. Okay. So knowledge. 2 moles of gas on left and only 1 mole on right. First mark, tick. Right, oppose. What did we do? We increased the pressure. Easiest mark in the whole thing, no one ever gets it. We increased the pressure. Therefore, the equilibrium will decrease pressure. Now, how do you decrease pressure? What do you favor to lower pressure? You're gonna favor less gas. Yeah. So favor to lower the pressure, favor side, equilibrium will favor, you need to put it in proper sentences, of course. Equilibrium will favor side with less gas, or fewer moles of gas, if you like. I don't really care. Next, shift. Right. At this point, we need to look at this. Favor the side with less gas. It's going to go in that direction. It's going to favor the side with less gas. It's going to go that direction. Shift left to right. Equilibrium will shift from left to right. The yield of ethanol will increase. Right. So that's a good thing. So if I want to make more alcohol, I am going to crank up the pressure. The question is, how high can we go? Sorry, that was terrible singing. Do apologies. How high can you go with this? This is a very special reaction, and you need to know this. The answer, temperature, 300 Celsius. Pressure, 60 atmospheres. Yeah. Now, just point out that you should go way higher than this. Do you know that they actually buy equipment that can handle 200? They buy the same equipment that they use in the Haber process. It's just easier. Rather than making a different one, they just buy the same one. Oliver, your camera's frozen with you yawning. It's hilarious. Yeah, 60 atmospheres. Now that's weird. Yeah, weird. Go higher. Yeah, they can go higher. Go higher. Is there another reason for the high temp? No, the high temp is because we know that the forward reaction is exo. Forward reaction is exo. Backward reaction is endo. If I increase the temperature, it'll push it back. This is a compromise. Yeah. Reasonable rate, reasonable yield. This is also a compromise. So go higher. We can't. Above, this is where my pen's too skinny. I've gone too big. Above 90 atmospheres, ATM, above 90 ATM, the ethene will polymerize. It'll become a plastic, becoming polyethene, which is a solid. Block pipes, explosion. Boom. Not good. So they turn it down to 60 because it's dangerous. Right. Now I've only got 5 minutes left. I just want to do one more. I want to do concentration. What I'm going to do is really want to do another one, get concentration done, but my lesson's running out. Right, go back to my learning objectives. So what KOFS stand for, we've done. Use it to explain shift, we still need to concentration. Conditions for some equilibrium, we've done partial. Yeah, half. Got others to add to. I meant the high temperature as a reason for high temp would increase pressure, and that's a good thing for yield. Right, remember that whenever you do this, can equipment be built to withstand high pressures and high temperatures? Yes, absolutely. But you can make equipment which can go to 1,000 degrees, but it's super expensive and not worth it. It's just not worth it, Jim Joe. Great question. Right, I'll pick this up next lesson. Going to end the lesson at this stage. There we go, mic's back. I will end the video here at this stage, guys. It's doing something really weird. There we go. What does increasing pressure increase temperature too, and will that affect yield? This is something you are muted, I know. Okay, so Jim Joe, I'm going to go through this. The high temperature will lead to a high pressure. So we do it we control them very carefully, completely independently. Yeah, whenever we do an increase in pressure, we'll cool it to maintain. I know that you guys know that if you raise pressure, you raise the temperature. If you reduce pressure, you reduce pressure, you decrease the temperature. We know this, but we handle them completely independent. Yeah, if somebody raises the temperature, we will have a carefully controlled system to maintain the pressure. Yeah. And we do that because we're trying to analyze what the best condition is. Once they've discovered that, they don't really care at that point, and they just set the temperatures and pressures what they need to. So, yes. The next one is, can equipment be built to withstand high pressures and temperatures? God, yes. So we can make equipment that can handle thousands of degrees Celsius. Can be done. Way too expensive to do for most companies. It's just not worth it. Yeah, these vessels run for 10 years constantly without being switched off. They have to be replaced by law. Well, if you were to make a piece of equipment that was, $1 million, it's just not worth it, because you're going to have to replace it in 10 years' time anyway, and you're not going to make enough yield, and a big enough increase in yield to make it covering the cost of your new equipment, so you don't bother. You can also make them take up to horrendous temperatures. It can be done. But again, the kinds of materials, the exotic metals that you'd be using titanium, tungsten, crazy alloys that are ridiculously expensive. So it's just not really worthwhile doing. It's all about in terms of equilibrium, we talk about this idea of compromise. For companies, it's about weighing up whether or not it's worthwhile, the cost of the equipment versus the increase in yield. We'll talk a bit more about that next lesson. I'm going to leave you guys be now. I'm going to end my YouTube video and say I'll see you guys next lesson, and I'll return to the Google chat, the Google Meet.